This is the fifth Beard Tribology Webinar. And today Fred Higgs from Rice University is going to talk, but I'll save more about that in a second. So we started this at the beginning of the year, 2021, but it's named after Ralph Beard, who helped us create the tribology minor at Auburn University. And there's a fund for excellence named after him to help provide scholarships for students in the minor. And we plan to do this webinar the first Tuesday of each month at 1 p.m. Central Time. So looking at the summer, we might take some months off in the summer, probably June and July, but we'll see, and then continue in the fall. But we'll let you know what's going on with that. The next one, we won't take June off. We're going to have. June is going to be Professor Andreas Rosenkranz from University of Chile. I think he's going to talk about 2D materials and friction, reducing friction, some more like cutting edge research in the area. So that'll be in June, and I'll send an announcement about that out as well. And then July and August, most likely we'll have to take off. A little about the tribology minor. We have a minor for undergrad students that's kind of unique. It's 15 hours of courses. There's a link. You can also just find it by searching on Google tribology minor. You should be able to find it. And we appreciate support from the community in creating that minor and keeping it going. Really, scholarships help encourage students to pursue the minor because it is extra work that adds on to their major. Then we also created an online engineering graduate certificate, which is good for folks who are in industry looking to just add a little background in tribology. We have a board that helps supervise and provides support for the minor, and it's an industrial advisory board, so that we're trying to get feedback from industry as to what needs are, what do we need to be teaching for industry, what topics are important, and that's really why the minor was created, to try to fill in that gap. And really appreciate Raj Shah and Maureen Hunter. They're the co-chairs of the board, and they helped to create this the webinar series as well. We appreciate support from several different companies and organizations who've helped support the minor and the webinar over the years. I'd like to ask you to use the comment section, the messaging for your questions, and we'll look at those after the end of the seminar and read them read those questions to the speaker. And thank you again for attending. So let me introduce our speaker. Our speaker is Professor Fred Higgs. He is the John Ann Doerr Professor of Mechanical Engineering at Rice University. I believe he's also Vice Provost. That's correct. You can correct me later. And he's also a joint professor with Bioengineering Department and a faculty director of the Rice Center for Engineering Leadership. He's a member of the ASME Tribology Executive Committee and an associate editor for the STLE Tribology Transactions journal. His Particle Flow Tribology Laboratory conducts coordinated high-performance computer modeling and experimentation. He's a fellow of the American Society of Mechanical Engineers. He's published over 100 papers and has been a research advisor for over 100 undergrad students, 30 master's, and about 20 doctoral students, and 5 postdoctoral students. He's married and has for 16 years and has 3 children. And I think it's been a long time. We've known each other since Georgia Tech. We were both grad students there. And so we've kept touch over these many years. It's always been a pleasure to see Fred from time to time at conferences and other tribology events.
Well, thanks a lot, Rob. So it's interesting to see Rob progress at Auburn. He was a PhD student. I think I was a postdoc there, and but I think we used to sit in on Shooter's class, or I was guest lecturing or something. There, Rob, he brings steroids to the smallest problem. He's very detailed oriented. So, he'll analyze the little pixel for friction and wear and lubrication, everything in a little pixel. He'll do that. So you guys have a serious scholar there. And I know I don't know if Ryan Combs is on here. He's a professor in physics, also pretty intense. He was an undergrad in my lab at Carnegie Mellon. So the scholars I know who are now professors at Auburn are quite hardcore, technical, and interested in wanting to get the problems right. So I enjoy keeping up with them on Twitter and all things else where they're announcing the progress. So thank you for inviting me to the Beard Tribology Webinar series. And I've been keeping up with you all from afar, so I'm honored to be invited to talk about what we're doing with Industry 4.0. Still keeping tribology is a key part of it there, but it's to be broadly interpreted from kind of a design for additive manufacturing viewpoint, and how we apply that to different applications like energy and bioengineering. So my lab is the Particle Flow and Tribology Lab, but now I'm a part of a center that we've started here at Rice called the Additive Manufacturing Performance and Tribology Center. But in my particular lab, the Higgs lab, we do experiments in modeling. So our PhDs graduate about 50-50 in experiments in modeling, plus or minus 10%. We've been a little more biased on the modeling in the 10% lately. But we characterize systems, we use modeling, we use experiments, and they go hand in hand in our lab. And so it's put us right front and center with this whole thing on Industry 4.0, which I will fully describe to you all. But here at Rice, and we have the Additive Manufacturing Performance and Tribology Center, known as the AMP Center. We usually have an annual symposium. We brought Rob here to speak, and other scholars from around the nation, a couple from outside the nation are here. But we're focusing on this problem, and one of the angles that we really look at is the Industry 4.0 problem. And so you think about the industrial revolutions, there's been, the first one was, there's an agrarian society, started adding machines there. Rob, can you see my mouse? Not yet, okay. We started adding up machines to that one. And then we started assembling machines together, right? Beyond agriculture. And once you assemble machines together to work in an assembly, you can now put together cars like the Model T. You have an assembly line. That was Industry 2.0, the second industrial revolution. And then Industry 3.0 is where we started putting software on these machines. And so everything became automated. But we've recently entered the fourth industrial revolution. That's where now you have sensors, ubiquitous internet, the cloud where you can put your algorithms somewhere. And you have data that's constantly streaming in. If you have sensors on the machines, so data can come into them, or they can sense their environment and send data out. You have algorithms that can interact with that data. And if the sensors are connected to the controllability of the machine, now you're talking about a new realm where data can interact with the machine, tell it what to do intelligently. You get rid of you minimize the humans all of a sudden, and you can do everything in the previous industrial revolutions and more. But because of the intensity of the data and what the information it can give you, everything becomes personalized. And hopefully I'm going to show you how that is and how we broadly interpret that there. So it's going to change everything. It's changing everything, the way people work and live and how products are consumed and produced. And it really comes down to a series of technologies here. Start at 12 o'clock, autonomous vehicles and robots, simulation-based engineering, digital twins, the Internet of Things, cybersecurity, cloud computing, additive augmented reality, the convergence of these things working together actually represent a new paradigm and not just basic disparate technologies. In particular, in this presentation, I'm going to bring some of this awareness to you, mainly in terms of where the blue arrows are. More of an additive, a little bit of massive data there, but more simulation-based engineering, digital twins, and of course the 3D printing, also known as additive manufacturing. Cloud computing and Internet of Things are implicitly there, but we're not fully there yet. We're not interacting in real time from remote, from the internet. So we're setting things up, but we're not actually there yet. So just talking about additive manufacturing, it's basically about, if you look at the traditional manufacturing, which is subtractive, you start with the bulk material and you just cut away at that bulk, right? With a machine, or it's a sculpture, happens manually. You get a three-dimensional object there, got a lot of waste, right? Once you cut these geometries. But let's reverse that around. You have additive. You have a little bit of powder material there, and then you piece it together according to the CAD. So you get a CAD for this three-dimensional object, and then you have a 3D printer that binds the object solid wherever the CAD says it should be. And then you build your three-dimensional object, and then you don't have that same waste, just a little bit of what you started with. The more intelligent you get about your starter powder material, the less waste you have. But there's also no geometrical constraints once you go from the bottom up, right? Because you can have tubes and orifices. If you think about it, we have a biological 3D printer, which one of my colleagues is working on. If you had no limitations to the material, you're coming up. You have little tubes, we might call them veins. You can have bone material for any geometry. You go from the bottom up, you can create anything, all right? And so where subtractive, you can't get the interstitial cavities that are there because you're subtracting away. And so the other exciting part are no limitations to design. I know it's gonna be hard to see, but zooming out big picture, I'm just showing the 7 main additive manufacturing technologies. Over here is vat photopolymerization, light-sensitive 3D printing, material extrusion-based 3D printers, material jetting, where you're actually jetting the material that you want to 3D print. We have a binder jet. This is actually a powder bed 3D printer, which I'll talk about. We have a metal binder jet 3D printer in my lab there, or it does any type of powder in principle. Then the ones that you probably hear more about are the powder bed fusion 3D printers. These are both powder beds. Then there's energy deposition, sheet lamination, others that you might not have heard of, but there's 7. These are the companies under here that makes each of these here. And I just want to kind of focus more in on the powder bed 3D printers. So we're still talking about powders. And powders are interesting, right? They're these particle materials, which my lab has studied now for 20 years. That plus a little bit of my postdoc. I've been about 20 years. And so you have here particles, have moisture between them, fluid can get in between them. There you can put stresses on them, little electromagnetic forces on those. I know Rob studies that with MEMS devices and other nanoscale devices. Particle size distribution, surface roughness, all these effects, cohesion, come into play when you're looking at powders here. And based off of this top view of this powder, you could imagine if you think about this in 3 dimensions coming out of the screen, we keep putting different layers on, you're gonna have different levels of porosity, which at the end of the day is bad if you're 3D printing a solid object. So your ability to understand the powder mechanics helps you understand the final one. So here's just a zoom in of the powder bed fusion. Basically, my lab looks at it in terms of the binding mechanism. Here, the binding is a beam-based binding, so laser beam or electron beam, and that's how you solidify the powders. But you could also have a fluid binder process, like in binder jetting, where now you have liquefied glue essentially, and you hit the powders, and then you form these what we call primitives, these solid objects there. And you do that intelligently, you understand what's going on. This printer here is in my lab. So I do want to dig into what we do with this a little bit. So it comes into, a point of view of these steps: powder delivery, powder spreading, powder jetting, that's the binding process. So I should say binder jetting. And then you lower the platform and do that all over again. At the end, you have a wonderful set of chess pieces. If my son is on this call, he'll get excited. We're just starting to get into chess here. But the action of the binding is also important. You have a lot of fluid particle interactions as these droplets come down from the binder jet. You have different binder jets. They hit them at different times. You have all types of particle ejection and particle coalescence due to the fluid there. And so I want to simplify that in terms of these steps. It's powder delivery, then you spread the powder, powder jetting, and then finally sintering. It turns out that as a particle tribology guy like me, that this just came right into our wheelhouse there. And so we had a hammer, we're looking for a problem, this came right to us. And so we're very excited about that, right? That's what PhDs are. We have students on the call. We're experts of this, but if you come into our expertise, we get very excited to unravel that problem and to help solve problems for industry. So let's look at the first, one of the first things I want to show you is powder spreading, what we've done with that. So you have a powder, we have a powder rheometer in our lab. It basically stirs powder and gives you the amount of energy it takes to do that. You can put air and fluids through it and stir it and look at the different energy signatures of the powder. It allows you to find out something about the rheology of the powder, the flowability of the powder. And what, in a new term that we brought into the AM community, is the spreadability of the powder. So here is a particular powder. Here is Ti-64, titanium 64. Here we're looking at it for different companies. EOS has a Ti-64, Arcam, Amatec. These are the first two 3D printer makers there. And here you can see the bulk flow energy. The amount of energy it takes to stir that decreases, right? And here's the first one. It decreases as you increase in the manufacturer's different powders, which have different particle sizes. And Rob can tell you something about, surface area to volume ratio. If you're increasing the size of the particles, the forces there between the particles are going to decrease. The surface force is going to decrease. And that's showing up in this energy parameter here. Also increasing the ferricity. If it's more aspherical, imperfectly spherical, then now you're going to have less contact. It's going to be less energy there. And then at a certain point, you get big enough, you reach a threshold where there's no cohesion anymore. There, so there's less energy when you're doing that. So all from this powder rheometer, we can find out things about the powder. And that's going to be important for our modeling, because here you have the physical rheometer. And again, as you get into kind of industry 4.0, it mixes, some people call it cyber physical, or the mixing the digital and the physical communities. You'll see how we do that in our laboratory here. So you have a physical rheometer there, which is a cylindrical vessel with the impeller blade going in the powder. We create a virtual form of that rheometer, or a digital twin of that rheometer, and then we do the contact modeling of the particles there, where we use the discrete element method to look at the interactions between the particles there. So we end up here with we end up here with a digital twin of our rheometer here. And basically, the red curve comes from this physical rheometer, and these other curves that are being generated are just tuning the micro properties of the powders to get them to match the energy signature of that actual physical rheometer. Once we get closer, you can see these iterations are getting closer and closer. Once we get closer to that red line, you now have what's called a digital twin of the powder there. And now you can use it into other simulations, like 3D printing simulations. And so, but we always are validating these things, and then we can get lost in having fun and optimizing in the virtual world or the computational world. So we have here's the X1 binder jet 3D printer in our lab. There we have different types of characterization experiments we do with it. We've built a small build plate here to make little coupons that we can focus our analysis on there. So here's the example of one. We look at, here's the the printer here has created these different cuboids, right? And remember, this is 3D printers, so we can put different process parameters literally on the cube. So, for example, theta, the rotational changes are at a certain level. The linear speed that the spreader comes across is U here. And then we have, for different operating conditions of that spreading condition here, we'll have different cuboids, right? So the first one, the bottom layer, once you put the second layer on, it's sheared, right? So you get to the top, you have a cuboid that's distorted. And then we get better, we improve it through trial and error. And then finally, you get a nice, perfect cuboid here by changing the quality of your spread. But we're going to do that in a more intelligent way with modeling. So here you can see we brought the cuboid into the lab with our surface optical surface profilometer. We can get surface roughness on top, and you can see it decreased here. We also can see it had no deformation. So we call this the winning cube. Ideally, you want a model that will tell you what's the spreading process recipe for this particular powder that you need to get this cuboid here. And then that's what you want the printer to do. So for every new powder that comes in, every lab now, you see those beautiful 3D printers? They are beautiful. They look like the Xerox machine, but they're not perfect like that. They're research problems always. So any new powder that's brought into your lab, it becomes a research problem to get to getting the perfect spread. We want to be able to have models to guide that. And so here we've done that. So here's a spreading simulation here where we have a roller rolling over powder. We're running a discrete element method on the powder. There, as the powder changes colors, you're watching the velocity magnitudes there. And then we can just look at the quality of the powder in the virtual sense. Then we bring machine learning in to connect the inputs. In this case, it'll be the spreading parameters like rotational velocity of that spreader, linear translation velocity, and then we input what do we want the roughness to be for the different layers. And then you get different outputs there, like porosity and surface roughness for the overall object there. And so then we end up creating these process maps here. In this particular one, it relates the throughput of the volume, the amount of powder that you can spread relates to the surface roughness. And you get these different curves. And it's a tractable curve that an engineer can come and say, oh, for this powder, I need red is the rotational velocity of the spreader, and blue curves are the linear velocity of the spreader. I need to get to this point to achieve this roughness at this throughput of powder there. And so we have that there, or you could program that into a printer and have it controlled there. And so, I would like to say to the students, we still are engineers. That's why I became an engineer. I was excited about it there. But so we try to always translate whenever possible to industry. And so in this particular one, all of that work goes towards a tool called Spreadify, where AI-enabled spreading recipes for defect-free parts, right? Meaning low porosity, no distortions as much as possible. And you're using physics to figure out what the winning recipe is from that process map. And then you would tell the printer, these are the parameters for spreading this particular powder there. So we come into a tool like this, Spreadify, click enter, which powder do you want? Type 6.4. Particle size distributions can be of different sizes. We'll say uniform. What's your particle size there, right? It relates to the amount of energy it takes to spread it. We'll say 250. So now we have a virtual avatar there, or a digital twin of the rheometer. It's spreading, doing the analysis there. And as it turns out, it gets to the end, and you can figure out, well, what do I now want to 3D print? Let's say a cuboid here. What is the geometry of the spreaders? All the 3D printers have different types of spreaders. To us, it's just a boundary condition issue there. And so you can have any of these printers, like the one in our lab, or the RCAM, or EOS. These are beam-based printers, so they get it through energy beams. And so here's one for an RCAM-like spreader. We spread that same pattern, and we would tell them what the spread recipe is, or what's the spreadability for this particular simulation. There, then that's fed to the 3D printer. Here's the X1, it's a roller, right? So as you're spreading this powder, look at the, I'm a tribologist, see the undulations on those surfaces there? So we are accounting for the surface roughness on the build plate or each lower layer there. And here's one from a textured roller, right? Does it, we talked about doing this. Basically, you look at the roughness of the powder, can you design a texture for that? You know, a tribologist like Rob would get excited. He'd probably say, hey, I can put a fractal signature. Actually, Rob doesn't like fractals. He likes multi-scale modeling, but which is a competitor method to looking at roughness. But can you figure out what is the proper texture on a spreading device to achieve a certain smooth roughness? All these things are surface interactions. These are things that a particle tribologist like me would get excited about on there. And so once we had that, then you say, well, let's do a virtual build. Let's look at the cuboid and see if it comes out distorted. And so we do a virtual build on that. So you have a 3D, you have a digital twin of our X1 printer going in and making this particular device here. Yet we haven't talked about the binding process there. But out of that, you come up, we always are coming up with these tractable process maps here. Again, you find the coordinate to achieve, faster printing, to achieve a certain roughness, low porosity there. And that's what you're trying to come up with there. We're just looking at different simulations there. And then you start your 3D printing. All this is done to prepare for the 3D printing process. Now let's look at that was all powder spreading. But what about the fact that if it's a binder jet printer, you have droplets coming down, forming that? Is there a tribology problem inside of that we can get excited about to optimize the performance? And there indeed is. So here's a look at a droplet coming down on two different powder beds. On the left, it's a titanium powder bed. On the right, look at that. It pulls these particles together, right? The fluid forces are pulling them together into what we call a primitive there. And we want to see if we could begin to look at that. So we created an experiment in our lab. We always got to validate our models. Then we can go to town with the models there. So we have a droplet experiment that we put here. We can drop powders in a controllable way, droplets, fluid droplets in a controllable way on different powders. We have high-speed imaging, so we can image that and begin to see if we can come up with a performance criteria to judge the quality of the binding. And so here you can see the top one, these are similar simulations, except the top one is going to have a faster droplet frequency, and the other is going to be a little bit lower there. So we let them come across, and you have the various types of binding that's going on with the powder that's there, right? And so, everything else, you hold that pretty much the same. What about if we have different particle sizes? How would that same high-speed video look there? So here we're going from small range of particle sizes to a large range. You should expect to see less movement of the primitives here, right? If you considering that type of a range there. And so here you see things are going on. You see some primitive formation events down there, but not as much as you see with the others there. So that says something about the resolution, right, at which you can bind different particles there based off of the speed at which you're moving around and the powder bed properties as well. And so we end up coming up, we have different trials. And so we start to have a criteria for judging it. And this particular one, we say that, well, maybe the best way to look at this is to put a bounding box around the different primitives that were formed there, and look at the fraction of that box that is formed into a primitive line there. And from that, we have high fractional areas. And so we could say something like trial number 4 was the best one because it had the largest fractional coverage area. But these type of things start to get us towards being able to judge what winning is when we go into looking at this as a model. And so let's get right into the computational models. I'll remind you that all the models that you see in my lab are done by hardworking PhD students, so there's no commercial codes used. We have all of our codes in-house designed from the ground up. One of the things we try to do for the tribology community is, we look at lubrications approximations, but we try to bring in like Reynolds equation, but we try to bring in the full 3-dimensional time-varying computational fluid dynamics. I teach a CFD class, so the students come in my lab ready to do this. And of course, we have the discrete element work that we talked about earlier, where you're looking at forces on particles there. Bringing that together is what you need to do to kind of look at modeling these different problems here. And so let's look at our approach. We've been using this volume of fluid approach to account for looking at the fact that you don't have the full domain in a fluid, but just some places in the domain have a fluid. So here's a look at just dropping a solid particle. This is not a fluid particle yet. We're watching just basic interaction, dropping objects on powders to see if we can account for what we've seen. In the community, we know there's particle ejection. You can see these particles bouncing out there. And then there's particle movement there. So our powder bed looks to be okay in how we're accounting for that. And we have the real properties of Inconel powder, which is one of the three-dimensional powders. So we felt good about that. But now we wanted to bring into effect fluid droplets. And the fluids don't hit everywhere. It's not fully immersed like most of my work that people have seen. And so we had to use this volume of fluid approach where you're looking at the difference in phases there. And so you have one phase might be air, one phase might be liquid there. And so you account for those different concentrations in different zones. And then you could track the interface between different fluids there. Then there's fluid particle interactions. You have fluids pulling on particles, creating a total capillary force, which is a function of the Laplace pressure force and the force due to surface tensions pulling on these particular particles there. And so now we're ready to look at a fluid dropping on a powder bed, not a solid particle, but this is now a fluid particle here. And we're looking at it for two different contact angles. So the angle between a fluid and a solid surface, we've input this as 30, and we've input as 150 here, more hydrophobic here. This is more hydrophilic. And so let's watch what happens when we watch the simulation there. This one here, a little bit more hydrophobic, so it comes back up. It's running away from these particles because of the high contact angle there. And here you look at the same simulation just from the top. And this is from a pure side view there. And you can see now, this powder bed is fixed for this simulation. We just wanted to look at the fluid behavior against a solid powder film, although the powders are not free to move on this simulation there. And so we kind of like what we saw there. So then we said, well, let's look at it if multiple droplets are hitting a powder bed. And so we thought that looked similar to what we've observed there. And so we said, then let's start to relax things. And so the first thing we do is we come in and try to look at validating this. And so here we looked at what was in the literature. Someone had two particles and had a liquid film separating them. And so you have different separation distances. And based off of the separation distance, they were looking at what was the force actually acting on those particles there. And so here's the solid curve from the experiments there. We used our simulation and saw that we could get a pretty good match with the simulation there. So it gave us some confidence of our fluid particle interactions. So now we said, what about it in a triparticle situation? We have three particles together. What about the liquid bridge there? And we saw, again, we're reasonable with our simulation, the solid dots there. We actually match closer to this solid evolver curve, which is a different way that people looked at, just looking at the energy between particles. We were closer to them than to the experiments there. We went back and looked at the literature, and it turns out from the experiments, they had doubts on determining what their spacing was. So we matched another well-known simulation there, and then the experiments expressed doubts in what's the true distance and the accuracy of that. So, we don't feel too bad about being off since the experimenters were not totally confident in their distance there. But so it shows us that we're able to kind of do this there. Here's a simulation where you pull things apart and you look at the forces that are on them, right, all the way to breakage. At the end, it breaks off. And that's where our simulation shows the forces decreasing as the distance between those spheres is increasing, and then it goes to zero as you break the fluid filament there. And so that let us know that we think we understand fluid particle interactions. Now let's look at it in a bed, fluid droplet hitting a bed, powders allowed to move freely, just like you'd have in 3D printing. And let's see what will happen there. So you have over here, this one, look here though, the top view. As it hits those particles, it begins to pull them together into a primitive, right? And the size of that primitive is the resolution that you can report. So you can imagine the different size particles and the type of fluid that you have all going to the primitive that you get there. And we're modeling this accurately, which means we can now start to do, you know, increased frequencies and linear translations and things like those, which I'm not showing in this talk there. But all of this is really understanding particle fluid interactions there. The last one I want to show just briefly is sintering. Are we working on that problem? We consider that largely a material science problem, although we're particle people. So we team with my colleague, Zach Cordero at MIT. And we have a joint PhD student, Lenora Grant, there. And we've looked at this problem of what if the binder itself, it goes down and can crystallize into little particles in between, little nanoparticles. So it comes in as a liquid, it crystallizes when it's heated into nanoparticles that can then fill the gaps between particles. Will that cut down on sintering? Because it turns out at the end of binder jetting, you have to heat up these systems and watch what happens to them. So when you heat these up, you want them to become solid geometry that won't move. But the problem is that they distort. So here we use this precursor that we put in, a titanium dioxide precursor, and it formed these necks, solid necks there, and it did reduce the distortion there. And so you have an untreated, this is what you normally get in binder jet 3D printing if you don't do a smart solution. And you know, companies like X1 and all those have their ways of trying to deal with this. And here's just a look at one with our technique where we put in a binder that can turn to solid particles. You do increase the creep that's there and the distortion that results there. So now that you can see that we pretty much can model the entire binder jet problem in some form, or at least we're involved with it. Let's apply it to a problem like energy. So you have geothermal drilling. Basically, you want to get down to where there's a lot of heat to be able to run different things. There's a lot of geothermal reservoirs in different parts of the United States. Well, this is an exciting problem for my mechanical engineering undergrads. I like to put up a thermodynamic cycle. Basically, geothermal would just bring you heat, right? And now you can heat your working fluid. And so your working fluid goes around to the turbine, generator, get electricity, goes to a condenser, condenses back out, you go around. So where you have the boiler, you would run geothermal heat free from the ground there. And that's what they do to create power from geothermal systems. To my thermodynamic students, like to show that. But back to the drilling problem, you have to get down there to where these geothermal reservoirs are. So you're drilling down there. And so you want to have a drill bit like this polycrystalline diamond bit communities for doing that. It's a clean energy problem. So not all drilling is bad there. So, you know, we have done a literature survey behind it. Young scholars, you want to get into the literature. Here we've looked at different experiments and modeling and and other things that you're doing with the drilling problem there. And it forms the design-for-additive manufacturing framework, which you'll see with us. So you start with the rock, you characterize the rock, you characterize the powder because you're going to give a recipe to a 3D printer. You get digital twins of those here. We do literally virtual characterizations. You can see we're crushing this rock here. And we're tuning the rock's properties just like we tune the powder in the rheometer's properties to get that powder there. Once you do that, you have a digital twin of that rock or a virtual avatar, same thing. And now you can put a drill bit in that, optimize for rate of penetration, get your nice process map, tell it to the 3D printer, you can print out a drill bit there. Here we have a drill bit spinning in fluid. We run the full CFD analysis ourselves. We end up printing these drill bits in our lab there. Notice there are different cutters on there, and the cutters, the different angles form the different types of PDC bits that you have. So here's a look at a drill bit going into a rock there. And so we have a rock that's there, we're drilling into it, we're accounting for the friction and the wear that goes into that. The wear in this community is called the rate of penetration. It's the money variable. The faster you go in the rock, the cheaper you pay, your costs are on renting all these drilling equipment there. And so we do different drills. We can look at what that means against experiments. there, and this is our in-house code, again, that we've made from the ground up, P-STAC, Particle Surface Tribology Analysis Code, so the T is tribology. And this is just a dry one. What happens when we put fluid in there? Here we have the fluid in here as well, being accounted for. And now you're drilling that rock. You're watching the rate at which it goes into the rock. It's known as the ROP, rate of penetration. I like to show this simulation. You see this? This is fluid pressure to my tribologists there. So we're looking at the fluid pressure under the drill bit, and it generates a little lubrication pressure. We take that lubrication pressure away from the weight that's on top of the bit. Weight on bit is a property that's in the drilling community. So we say the weight on the bit is taken away a little bit, reduced by this fluid pressure that's there. And so you have a new resultant weight on bit there that you need to account for when you're looking at your rate of penetration there. So we are solving for the lubrication problem right there beneath that drill bit as it's going into the surface. And so we end up with experiments and modeling, something we're still working on here, getting the exact same experimental system. We're still working on that, but we can do it for lower loads, and we can do it at basically the same speeds there. But we're working towards that, and based off of getting that match against the experiments, you can then begin to change the design of your drill bit to achieve a certain rate of penetration for different types of fluids that are there. So, for example, we can look at the wear on a cutter there. We can look at that per unit depth there. So we have properties that are in the cutter. We can account for that. We can then say, well, based off of these parameters on your drill bit, you can have a certain rate of penetration. These are just switching input and output parameters. So we run our full physics-based simulation. We run a few of them, and then we start to have machine learning to guide the physics-based model. It's running our physics-based model to get a bunch of parameters, and then it generates a mapping between those two. And so we get something like a blanket like this, where you're looking at, you have training data. First, we validate our physics-based model, and then the model we now say is our key data, right? And then we throw out a few points to match for different angles on the cutter, on the PDC bits. We look at the wear volumes there, and we test that, and then you watch the points there. You have some data that you train it for. You have some data that you test things where you're blind on things there, and then you see if you have a correlation. We get pretty good correlation there. Now that means you can get away with your physics-based model, put that away. Now you have the machine, you have the neural net that can now represent that system there. And so you end up being able to now generate something like this, a process map. We love our process maps, where here, the coordinates of red and blue go with the different cutter angles that are on the PDC cutter there, and you have a final drill bit wear and rate of penetration that you could predict. So the design parameters are red and blue, and the performance parameters are actually weirdly enough on your X and Y axis. So you change the design parameters, you get different levels of wear, different levels of rate of penetration. So now you have lifetime prediction actually there, performance in terms of rate of penetration is there. And so you put all that together, you got these avatars there, virtual labs you're running, machine learning, and you come up with the process map. That always guides the engineers on what to do, whether you're putting it into a machine or you're just telling someone what the parameters, the design parameters need to be for a bit. And so again, we try to get this into something tractable. We keep our students excited about trying to constantly translate things. We're not scientists only, I should say. We're engineers, so we want to get this into the marketplace. So here's the Tribology here, and so you can press on Tribology, and so it says, well, what kind of rock do you have? That's a different geomechanical property there. What about the grain sizes in the rock? What are the particle sizes in that particular rock there? And so then you do some characterization tests, right? We're always doing these characterization tests so we can micro-tune the properties of whatever it is, in this case it's a rock, to see when it matches that. And then we could do rate of penetration tests virtually, and now we could look at performance. We're now ready to go and generate a design chart of this particular drill bit here. So the design chart there is done through machine learning. We end up with this chart here. Now we could vary the parameters on the drill bit that are personalized to a specific rock there to get a certain rate of penetration. We can start our well planning. Depth of well, rotational speed within the well, weight on bit. I talked about that earlier. When do you fail, right? You do a lifetime prediction, you need to have a criterion for when something fails. And then you'll know that, now my cutter is worn this much, so now it's failed. And then you can calculate times like when you want to replace your bit. That's what they care about in the drilling industry. So here you can see now your drill bit is automatically being varied according to these parameters and figuring out what's the winning drill bit design for a certain rock property. The property is usually called lithology in the drilling community. And so it tells you, well, for this one, you need these angles on this drill bit. The bit must only be replaced once. In this one, we ran a little short within our lab. We have a drill bit, a drilling rig in our lab, so it's a lot thinner than the one that we get in the field there. And so you're constantly looking at mixing the digital and the physical. And so you end up with this, if you notice this pattern here, this is designed for manufacturing framework. I'm characterizing digital twins, run multi-physics simulations, come out with a tractable process map, then I tell my printer what to do. And that's what Industry 4.0 is. It's all about personalizing. In this case, it's personalizing the drill bit here to the rock here. And so you can think of way out in the field, you might want to rapidly print drill bits for the different lithologies that you're seeing downhole. Same bit, same piece. Now we're moving on to orthopedic prosthesis. Notice that everything is the same here, except my actual component is a femoral head, right? You think of a drill bit, you think of a artificial joint, you have a femoral head going into an acetabular cup, and we can do this analysis here. And we come along with the personalized hip that you can 3D print. So it's still personalized, but it's personalized to the patient now. Here's what I mean. So you have a drill, you have a femoral head, right? And this artificial joint. My father has an artificial knee, right? So this is artificial hip. It goes into this liner there. Why am I looking at the problem? Because you still have surfaces interacting. You get wear debris there. We love this problem as tribologists there. And so it ends up being a problem where you have experiments and modeling. You have partial contact and fluid contact there. We call it mixed lubrication there. And we're going to be able to model that there. And so it ends up being this problem that we've called the particle aminic mixed lubrication problem, where you have partial fluid and you have particles in that interface there. And so you have to solve the fluid mechanics, the solid mechanics, the wear problem, and the particle problem, because they are agents of wear. And you end up figuring out the equilibrium of contact between the solid and the fluid. Here. No, I'm running out of time here. So here we solve the lubrication equation this time, because the main problem is the femoral head in the acetabular cup. The overall problem is a lubrication problem. We can account for contact with different means. In this case, it's Winkler model. Here's a person. They can have different motions. As they move, they have different load signatures. So here's when the person is walking, they have different load profiles there. They have different movements. We can put all of that as input in our system, in our tribology system here. And we can do something like, well, let's say, what do we texture? Something. You have wear debris, which is a problem with orthopedic hips. Maybe you can get the active wear debris to come into these cavities and it lowers the wear. It's just a hypothesis because I'm in a virtual realm, right? And so here we could try this hypothesis, see if we have inactive debris, and let's look at it. Here's the femoral head, right? It going into a cup. This is texture, running that hypothesis. Each of these little things here, the little fluid pressure in the cavity, right? Red means it's high pressure, it's a lot of lubrication. And then here's gonna be the wear there. So we're gonna watch the wear project onto the cup here. So as you're rotating that, you can see that femoral head rubbing in the cup there, and you're actually watching a projection of the wear onto that head. It's actually happening on the cup, but we're showing where it would happen on the projected area on the particular head there. But you're watching the evolution of wear as a person is walking there. And so we could account for that problem there. And so then for different walking, we can see different levels of wear there. The highest wear here for walking upstairs, turns out more wear there than just walking fast or walking downstairs. We can look at instantaneous wear for different motions of you walking. There are different positions of you walking. And then we come away with something like this. Always, well, who's the winner there? Well, here, you know, based off of this surface texture, you can learn lower is better here. And so here's material being removed. This is wear. So you want low wear. But over here, this is the amount of particles that are being put into those little cavities there. Higher is better there. You want more active debris being deposited there. And so then you come out with something like this, Industry 4.0 orthopedic surgery, right? Where now you have a particular person that comes in. This is an osseo integration simulation, bone ingrowth. Another problem with the collaborating in our lab there. But here, the powder that you can 3D print with, you can watch the rate at which the powder geometry allows bone to ingrow into that powder there. Let me stop using my mouse, it's coming up. So, so once you know what the best powder system is for this particular problem, you can then send it to the 3D printer and print your orthopedic joint. Your orthopedic hip joint is customized to that patient there. So it's a kind of the new age of that. I just want to leave you really quickly, leave time for Q&A here. This is one that we're working on here with lifetime prediction with ball bearings there. Again, you have a ball bearing, you can use deep learning. We realize that we're thinking about buying sensors. We realize that our tribometers themselves are sensors. So let's look at the 4-ball tester, and we can get data off of that. We use different things. We do interrupted tests to look at the evolution of wear on one of the balls there. You see seizures about to happen here. This is friction over here. The blue is the remaining useful life, right? So you get a lot of friction, and then you get wear. You have a certain wear criterion. Let's call this our wear criterion. Once you hit this, we say it's failure, and so now you can predict failure. But bringing in machine learning to predict it just on the data is one thing that we're starting to look at. I don't like that problem because it puts my modeling out of business. But we do have to look at it as scientists here. And so we're looking at now bringing in massive, sorry, go back. Oh, okay, so looking at massive data, seeing if we can figure out what are the parameters needed to predict when lifetime will go to 0. You're starting to do lifetime prediction, just like we could do with our models here. But we're taking in more data here. So it's a new problem we're looking at effectively. Okay, so we're doing all types of engineering prediction by mixing modeling and experiments. It brings about exciting questions with Industry 4.0 that's not been fully realized. And we're wondering, I'm still an educator. I also have a leadership. Rice has a leadership center. I like to think about, will this change how we educate and how we lead? We think it will. We think it will. So we think it's all about a new type of engineering leader here, a person that is now thinking in terms of the data and how that will change the final product there. And so we've actually created a master's degree around teaching a new way to manage with the Industry 4.0 lens, which is informed by my tribology research on looking at the next generation of bringing Industry 4.0 into tribology, and what does that mean for products there. So we're looking at this as well, and so we've created a degree around this. My computer's lagging here. So, all right, I think I better let it stop at this one. The next slide is the final slide, but my computer's just starting to lag there, Rob. So, all right, there it goes. So I appreciate it, and we have a new master's degree on massive engineering management leadership for Industry 4.0 leadership. So we want to create the next generation of leaders. All of it is informed by what we're doing with Industry 4.0 there. and it's informed by tribology. Yeah. So thank you. I'll take questions now.
Thank you, Fred. That was very impressive. A lot of great simulations and a lot of food for thought, a lot of different areas. See, if anybody has any questions, you can write them in the chat. Let's see. So someone might be thinking about something or writing it out now. I had a few questions. With the additive part, you talked about, you know, the quality of the builds. Could you also look at the efficiency, you know, how much, because one thing I've heard recently is additive manufacturing 3D printing is not very energy efficient. So maybe, you know, balancing the quality with the energy used to make something.
Yeah, certainly that's true. We started to talk a lot more with 3D printer manufacturers. We're starting to recognize that all of the wonderful outputs from our models are ahead of what the machines are. So we're like, hey, look, if you could do this with your spreader, you're going to get much different performance. And they're like, we can't change that. Right? And so we're looking for fully variable machines. And there's a particular company that's starting to look at, they're putting sensors on everything. And so, for example, you can imagine with spreading, we've looked at frictional torque. As you know, frictional torque can be looked at in terms of energy dissipation, which is going to change your powder bill. Of course, you have waste. We believe that you do trial and error. It's very expensive there, and you're doing more tests as well. We think that having model-guided experimentation, getting to the winning solution faster, will save you time, money, and as you just said, Rob, energy there. So we do think that this Industry 4.0 perspective, and that means getting data on everything and introducing digital twins and simulation-based engineering, which means getting the winning solution a lot faster. The convergence of those is where all the spoils are in saving energy, time, and money.
Thank you. So we do have some questions now. Someone said great presentation. For the machine learning, do you plan out the simulations to generate data sets that prepare a good training sample for the neural network? I don't know if I read that the best way.
That's a good point. So there's Ryan, a former undergrad researcher from my lab, and who actually is the first undergrad to have a first author journal publication in my lab. So I'm happy to see that ended off well for him. So that means we have the barometer on what's great, and Auburn has found it. So, yeah, so that's a good point. You're really talking about treating machine learning like a virtual experiment, like a design of experiment point of view. In that case, you start to think about being smart about your experiments there. We do a little bit, but we don't do it in the classical sense of design of experiments. We do it more of we have some physics-based modeling. We do a few different points. That takes a lot longer, right? We have a few different points. We try to find an envelope of interest. And once we have that envelope, then we say, all right, let's run a few in between that envelope there. And then let's put machine learning to try to interpolate between these and figure out the nonlinear relations between all these points. And then we end up with a complicated blanket. And from that, we get our process model there. And now we have a neural net of the virtual system. Of course, we have to make sure the physics-based intensive model is validated. And then we go into this world where we can answer your question there. So we have to start to do design of experiments on the modeling to figure out what's the best places to probe the most sensitive parameters and things like that. We're trying to get there, but we're not there yet. So we still eyeball things in the modeling. This can get confusing to people because I'm using experimental language talking about physics simulations there. but it becomes that. We call them computer experiments in our lab. When you have all these parameters in physics interacting together in a multi-physics simulation, it becomes like a computer experiment where you don't know the end of it. You're not just solving a PDE. You're solving, you have event-driven phenomena, and you can't wait. You have to wait until it's over to see what happens, just like you have to do in an experiment. So once you enter this virtual world, you're watching things on the computer in a similar way.
Yeah. Are you looking at surface treatment of the powders?
Yeah, in the picture I showed with the powder rheometer, I showed a lot of different of the same powders. I showed pictures of them. We can look at the quality of the asphericity. We can look at the roughness that is on them. For example, that's how a bunch of mechanical engineering tribologists realized, oh, gas atomization, now I understand it. We look at their particles, they look perfect. They're perfectly spherical, they're perfectly smooth. Okay, gas atomization is the way to go if you want perfectly looking particles there. We learned that by looking at these micrographs there. And we can put roughness on our simulations as well there. So yeah, we have people that come and visit our lab who just care about the particle treatments on these particular powders. To us, it's just another parameter that we put into our model, and ultimately want to look at the final performance there.
Yeah. Are you able to include a lubricant in the simulations to study the impact of lubrication in either rock drilling or artificial hip applications?
Yeah, we did in both. When I showed the simulation of the drill bit, and at the bottom, I mentioned that we're looking at the hydrodynamic pressure. That means you're looking at a lubrication-based pressure right there. And this is great. So we can now, because we have the drill bit, the fluid, the rock, right? And you're accounting for things like rate of penetration and the wear of a drill bit there. You can probe these questions. If you're looking like the SPE literature, it's usually like isolated studies on viscosity of the drilling mud, which is what you're getting at. Of the drilling mud is the lubricant in that community. But ask a question about how does the rate of penetration relate to the pump power of the lubricant? You could do that in our simulations because we have all of these physical phenomena interacting in one system. It's not simply an isolated PDE on one of the phenomena like lubrication. Lubrication is just one in a full simulation. So you can say something like, what does the particle, what is the strength of the rock and the viscosity? How do you coordinate those to get a particular rate of penetration? We can ask those type of questions. It's in a computer experiment. We have to either make a process map or something, right? Because these are not just solving one PDE there, but we can get that information. The same for the hip. The viscosity is in that Reynolds equation that we had on the hip. So you're effectively looking at the lubrication quality between the femoral head and the joint, or like my father, the knee, right? You have the knee, the tibula. It's still a tribology problem there. You can look at that synovial fluid effect. For the particular patient, right? We bring into the dynamic activity of the patient. All of this in this industry 4.0 world, it ends up being, man, I got all this data and I can optimize everything. Oh, I'm gonna personalize everything. So you get from mass production to mass customization because the data can tell everybody, every instrument, what you need to achieve for a certain end product. Everything becomes personalized. And that's going to change the way teams interact, right? Like, why are we taking all day to get a perfect drill bit? Get that drill bit into the field, get data off of that, and then just get a minimum viable product into the field, get data off of it, and then learn from that. Back into the lab. Let the engineers watch the data of how people are using it with sensors. And now you come in, you approve your design there. It's going to change things. You need to be agile, smaller teams, leaders on every little team there. That's why we think we've had to look at it in an educational point of view as well. Creating that kind of management.
Thank you, Fred. It's been fascinating. Let's see, we've got, I think that's about it. Are they printing drill bits now?
They are. It's mainly a research problem. They're not putting it in the field.
Okay, yeah.
But you know, some are there. Some are very excited. I see I see a few of them are at your seminar, but in terms of thinking about Industry 4.0, bringing that lens to the problem, they're thinking about it there. So.
Unless anybody else has any last minute questions here, I think we're about wrapped up. I greatly appreciate it. I don't know if I asked you, but send me your t-shirt size and I'll send you the minor t-shirt. I'll send that to you.
I'll do that. I'm all about t-shirts. So I'll do that.
And
t-shirts.
I greatly appreciate it. And it was really a great talk and a lot of interesting things in there.
Thanks, Ron. Always good to see you.
Hopefully we'll see you going to the STLE meeting.
I'll be there.
Virtual meeting.
Yes, I'll be there. One of my students, Josh Wagner, is presenting a talk, the detailed talk on the binder jet. I only showed a few particles interacting. He's going to show the entire binder printing process there.
Okay, great. So I guess I'll see you virtually there, but hopefully next year we'll get back to normal and have some real meetings. All right, great. Have a great week. And thank you.
Thank you.